Hello everyone, my name is Viraj, and today's video is all going to be about the post-contest discussion for Leetcode Weekly 427. We'll be discussing all 4 problems. So let us begin. You have problem 1, transformed array. Very easy problem. You're given an integer array nums that represents a circular array. Your task is to create a new array result of the same size following these rules. For each index I, perform the following independent actions. If it's greater than 0, then start at the index I, move numi number of steps to the right in the circular array, and then set result of I to the value of the index where you land. Okay, great. Now, if it's less than 0, start at index I and move absolute value of nums of I steps to the left in the circular array, set result of I to the value of the index where you land. And if it's equal to 0, simply set result of I to nums of I. Return the new array result, and then now they have defined circular array. It means simply that if the nums is circular, moving past the last element wraps around the beginning, and moving before the first element wraps back to the end. Okay, so very simple problem. Let us generalize this quickly. We start off with an n-sized array. Let's say A, you have the elements A0, A1, A2, A3, so on till the last element, that is A of n-1. Now, there is a result array that you want to create. It has the same size, so same initial empty places, which I later would want to fill. And how do I fill them? Very simple analogy. They are saying there are 3 conditions to this. Let's say you're standing at a number, you start at the first number, and you start off with the first index, that is index 0. You want to fill this index 0, but what do you want to fill it with? The argument is, the number that you are currently at, that is A0, if it is greater than 0, you will move that much amount of times to the right, that is right movement. Wherever you finally land, you will place that number there. So for example, A3 was a value of 3, so I would have moved 3 places, 1, 2 and 3, and landed at A3. Sorry, A0 was a number 3, so I would have landed at A3, and I would have made A3 come at this location, that is the first place. Similarly, if I would have been standing at A1 and let's say A1 said that the number is 4, so I would have moved 4 times, and whatever was the number I would have finally landed on, I would have made that number come to this location. So this is condition 1. If you think that the number is positive, that is greater than 0, you want to make a movement that is to the right. Now what happens if the number is less than 0? Same analogy, but you now want to move to the left. Let's say A1 is, let's say 1, so you would want to move 1 to the left, and then whatever is the number you finally land on, place that number at the current index you're trying to fill, as in this, let's say this becomes A0, and so on. And the final condition to this is, if let's say your number is actually 0 only, then you don't move anywhere, neither go left, neither go right, just place that number itself at the location. So if A2 is, let's say 0, then I'll simply place A2 at the second index. Now a very simple catch over here would be for you to ask, okay, what happens if I am forced to move so much to the right that I jump across the boundary of the right location? Or maybe the movement was so much that I have to jump so much to the left, I cross the left boundary. That is why they have actually quoted a term over here that is saying the circular array is present, or the nature of the array is circular. What does that mean? If let's say you are standing at this number A1 and it is less than 0, so it forces you to move to the left as an absolute number of times of A1, by the way. So let's say it makes you move 1 time, then you are at the first location, then maybe it also makes you move 1 more time. Now since there is no location before A0, your argument would be, where do I move? The circular array nature will say, don't worry, if you have crossed the left boundary, circulate back to the last position and make your jumps forward. So it sort of makes like this, that you're going like this, and then you come back and like this, and so on. You continue on your path. And same thing happens in the right manner. If let's say the right makes you compulsorily go out of the right boundary, let's say something like this, and then you're trying to jump outside the right place, don't do that. Make a circular path back to the first location. This is the circular nature of the array. Okay, so let us see an example now and understand this very simply. I'll just take the first case, 3, -2, 1 and 1. Okay, so 3, -2, 1 and 1. So you have 4 places to fill. You start off, the indexing are 0, 1, 2 and 3, and this is 0, 1, 2 and 3. So at the 0th index, the value is 3, which is positive. So you want to jump 3 times to the left, and the number kept after jumping 3 times should be placed over here. So we jump 3 times, the number kept is 1. So we simply place the number 1 at the first place. Then you are at the first index, it focuses to jump left 2 times since it's minus 2. So absolute of 2 is minus 2 of, absolute of minus 2 is 2. So you jump 1. And then since you don't want to go outside this left boundary, you make a jump like this. And then you make 1 jump back to the last position because it creates a circular way. And then you land at the number 1. And number 1 is where you land. So you fill this place as number 1. Similarly, you are at the second location, it forces you to jump 1 to the right. So I'll jump again. This number is actually 1. And I'll put a 1 over here. And then finally, index 3 makes me jump 1 more to the right. So I know there is nothing as right. So I'll make a circular right as in come back to the first location, that is 3. And I place a 3 at this position. And this is how I have finally created an array that looks like 1, 1, 1, 3. If I cross verify this, yes, the answer matches. Same thing will happen if you also solve the example 2 on your own. Okay, so this is a very, very simple problem. Now, why is this more simple? Because if you look at the constraints are very, very low. So for a beginner, you can actually brute force the solution out, as in just make the simulation happen. What if you stand at an index I and you actually make the jumps, you go right, 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 so on, so on, so on. We can understand that every number is only to 100, negative 100 to 100 limit, and the length is also in 100 order. So I won't take a lot of time, or basically I would take some time, but definitely within my general limit so that I can find the main answer. But since we can discuss a very optimized solution for this part, so we are quick enough to calculate what is required to fill at every place, let us do that. Okay, so now this problem, if I want to optimize this further, this problem has a very simple thinking to understand. You are standing at, let's say you start off, you are standing at the A0 number, and you want to find the number that you fill at the 0th index in the resultant array. Now, you can simulate this, of course, that if let's say A0 is positive, makes those jumps, whatever is the number of required. Let's say after this, you want to again come back circular, okay, make some more jumps and so on, so on. And finally, you land at some location which you say, okay, this is the number that I want to put. Or the same thing that happens in left and so on, so on, so on. Of course, this simulation is brute force. What if I want to calculate this directly? So let's observe this with a simple diagram. You have the number A0, okay? And let's say these are the final places, and then this is the end, and this is the start. So if let's say A0 makes you jump to the right, what will happen is you will jump like this, like this, like this, like this, like this. And then if it makes you again jump, so you will jump again like this, come back to this location. Then you can say that like if you, okay, so something like this. Yeah. And then if you observe this very carefully, I'll be jumping again that much amount if let's say it was there. And let's say maybe I stop at this location. So this is the number of steps that I have to follow. Now understand this, that this whole thing, this whole place that I finally fell to, starting from index 0, this is index 1, index 2, index 3, and this becomes index 4, I can directly be there. Now I can understand that the array or example I've taken has n equals to 6. How can I directly be there? First of all, I need to remove all the redundant loops that I might follow. So over here, you can very well understand that you have one loop, this one loop, which is making you go to the last position and then come back. So a concept that is going to help us do that is actually modulo concept, right? Because if you take modulo of a number with some other number, then basically you remove, like you make, if let's say you write A modulo B, then this is going to force A to belong to the range of 0 to B minus 1. So let's say if A was a very large number, it's going to become very small, or specifically in the limit of 0 to B minus 1. So this is very helpful for us. Why? Because if n is 6, you have 0, 1, 2, 3, 4, 5. So this is 0 to the 5 range. Now, you know there is no other number that you want to land except the indexes from 0 to 5 range. So what if A0 is a very large number? Let's say A0 is, let's say 98. You of course know that there is no index such as 98. How would 98 be actually covered is you would make a lot of loops and then come back to the final location where you would have kept. So how do I remove those loops so that I make my operation quicker is I can take 98 mod 6. And when I actually do that, I will be left with 3. And what will that indicate? That will indicate that I would want, like after all the loops that I could have created, I would have landed up at the location that is the third index. So this is sort of a visualization. You can pause the video, do this with a pen and paper and realize this looping part that I'm talking about. So first of all, I can take this whole 3 into picture. That is one thing. Now what might happen is after that you are standing at this 3 location. This is with respect to 0. So I haven't added whatever ith index for theirs, or I haven't generalized the whole concept. If I generalize this, what would happen is you would say, okay, let's say the steps that I want to take is AI value. So it would not be AI exactly, it would be AI mod n. This is to remove the circular, all the redundant circular things that you do. Now you want to find the final index where you land at. And you want to find it with respect to currently if you're jumping right. So the index that I'm standing at, let's say this is I, the current index, plus I do steps. That is the number of steps I perform. Now what might happen is after you have performed the number of steps in this current I index, you might still go outside the right boundary. For example, what if you were starting off with a location that was here? Or even better, let's say somewhere here. Let's say this was the blue location you started off with. If now you would have landed the steps to be 3 and you add 3 again, you still jump out of the right boundary. So you again want to make one more loop. So the same logic I can actually write over here mod n again for me to again stay back in the limit of 0 to this 5 range, or specifically generalized by 0 to n minus 1 range, 0 to n minus 1 range. And finally, this is actually the place where I will land at. So all this calculation, this quick calculation of modular arithmetic has made my life easier, and I have quickly calculated in constant time period that I want to land at the index, that is ind, just a variable that I've named. And then everything is very simple. All I'll do is I'll make my result of I equals to that array of index value. Okay, so this is the case that has been tackled for a positive value. Now, of course, I don't want to discuss if it's equal to 0 value, because in that case, it's very, very obvious. You just want to write this line as it is, as in result of I, sorry, not this line exactly. You'll say result of I because it's the same number. So you'll say result of I becomes equal to array of I. So this becomes the equal to 0 case. And now we have to discuss the less than 0 case. Now this is again as the same case. This is something we want to do just how we understood the right answer. But now there is a small catch that would be there. This is very, very important for beginners if you are new to modular arithmetic. First of all, the steps would be as it is, because of course you would want to make that much redundant, like you want to remove those redundant loops. So I would not directly take a of I. I'll say absolute of a of I because a of I was a negative value. Mod n. So this is again steps. This is fine. But now when I want to calculate index, ideally it should make sense that I have I minus steps, and then I can take directly as mod n. You can understand this by the same logic that I was doing it at this line over here, second line over here. But this is not how things might work, because what would happen is I minus steps, that is going to the left hand side, this value might become negative. So by modular arithmetic, that is something like this. If you do a minus b mod, like mod n, then you would have to do it like a mod n minus b mod n, and then you add back one more n and take a modulo again. This is sort of a small trick that we do to keep the inside bracket positive. So to do that, I would do the same thing. I can add an n over here, the div n over here value, because that is going to make sure that I still now am in the positive range of 0 to n minus 1, and then take a modulo n. This is a very, very important concept of, again, modular arithmetic. And then, yes, I've landed at the index. So same line repeated at this location also, good to go. So this quickly gives me the whole result. I don't have to brute it out. Now, of course, this would not be very, very beneficial in this question if you understand that the time constraints are very, very low. You can, of course, perform brute solution. But then what if the question demanded you for a higher value of n or for higher number values? Then you would have, of course, wanted a solution that looks like this. Hence, this makes the best case. So let us look at one of the examples quickly. I'll just take the same example. You have 3, minus 2, 1 and 1. What you might do is, this is index 0, 1, 2 and 3. So because this is 0 and this index 0 and this is the positive value 3, so you do 0 plus 3 and then you take a mod n again, which is actually mod 4 in this case, which directly gives you 3. So fine, at the index 3 is where you land, and at that location the number 1 is kept, good to go. Next time you will say, okay, I want to do something because this is a negative value. I would do, first of all, I'll say, or sorry, the final index value becomes, this is 1 plus, then the steps becomes positive of this or absolute of this, that is 2. And then you do again a plus n, so that is plus 4. And then you take a mod n with this. So this is like mod 4. So this becomes 1 plus 2 plus 4, that is 7. And 7 mod 4 actually gives you 3. So you'll land at the third location, which is making sense. So at the number there is actually 1. So you place a 1 again. And similarly, you fill it. So you will actually receive the answer back, that is 1113. Okay, so you might work out a different case to fully grasp this whole logic. The main idea over here is, first of all, remove the redundant loops, very, very quick, and then modular arithmetic is used. The direct addition case is simple because over there rules are very, very simple to visualize. But if you actually take the second case, you have to cover back that difference. For that, you need a plus n again, because I minus steps as a value might go negative. Okay, let us see the code now. Just how I explained the pseudocode, same thing. Take the input, take the size of nums, create an answer array, n size, start with the for loop. If it's 0, directly that number. If it's greater than 0, first take steps, that is mod n, index, that is I plus steps mod n again, and then dictate answer of I as nums of index. And if you feel that you're going to the else case, that is nums of I is less than 0, same thing, just absolute this time, and I minus steps plus n to stay back in the positive range, and then you make answer of I equals to nums of index. Then return the answer, and this is going to work. Now, what is the time complexity? Very, very quick. This is O of n order, and inside this, everything is pretty much constant, which means that even if n would have gone in a larger boundary of, let's say, 10 power 5, 10 power 6 order, now your question is very, very fast. The time complexity simply becomes O of n. And what about the space? I'm only using some space for the, you can say, the amount of space for this nums array to come into picture. So that would be O of n. Again, very, very fast. If we submit this out, this is going to work for us. Okay, so very fun problem. Let us move on to the next problem. Okay, so you're given an array points where points of I is xi, yi, representing the coordinate of a point on an infinite plane. Your task is to find the maximum area of a rectangle that can be formed using 4 of these points as its corner, does not contain any point inside or on its border, has its edges parallel to the axis. Return the maximum area that you can obtain on -1 is such a rectangle is not possible. So this is a very visualized based question. And if you, before even starting the problem, see the constraints, they are very, very small. You just have maximum 10 points to consider. Now, because you only have just 10 points to consider, and if you just visualize this question, you can understand that I would want a brute force solution in this question during the contest. All that we are trying to find is on the 2D geometry, the points that are given to me, as in, let's say this case, 1, 1, this is this point. 1, 3, this is this point. 3, 1, this is this point. 3, 3, this is this point. I just want to connect some 4 points so that I create a rectangle, first of all. So I have 4 points. I mark it off as corners of the rectangle, and I create a rectangle. Now, of course, that rectangle should not have any other point inside it. All right, it should be a free rectangle. You can say there's nothing falls inside it. So that is the second case. Again, this is if it falls inside it also, it's wrong. Or if it even falls in the border, it's also wrong. So you just need 4 seluded points which create a rectangle for you. And then you want its edges to be parallel to the axis. So we don't want this rectangle, let's say, to be turned to some angle. Imagine that this rectangle as a whole was turned a bit to the left, a bit to the right. No, over here you can see that all the edges are parallel to the axis. So this edge, this edge, this edge, this edge, this edge, they are all parallel to the x and y axis. So this rectangle is sort of perfect for us. It follows all 3 conditions. And if that happens, if I'm able to create such a thing, then I just want the maximum area out of all such possibilities of 4 points that I could have taken. All right. And now when I said the word possibilities, if you understand example 2 and if understand example 3 quickly, and example 2 obviously creates a -1 for case, because you cannot create a rectangle over here. Like if you would have wanted to create a rectangle that is outside these 4 points, this middle point over here, that is actually 2, 2, will come between or inside, that rectangle, which violates the second condition. Not great for us. And then example 3 creates such, like if you want to take again these bottom 2 points with the top 2 points, then these middle 2 points that is at the index, in the coordinate 1, 2 and 2, 1, 3, 2 are going to actually lie on, you can say, the rectangle itself on the borders. So that also violates the second condition. So if you quickly understand the examples, which are by the way very, very easy, all that we have to understand now is how do we solve the problem. And as I said before, since the points length is very, very small, for a beginner based question, you can understand that I can brute this solution out. When I said or coined it the possibilities, all that I would want in this question is I just explore the combination of all 4 points or all possibly 4 points, you can say not paired up, quadrupled up together, and this check whether first of all they create a rectangle. If they do they have any point inside that rectangle? And again, are they parallel or will their edges be parallel to the axis? If all 3 points checked out, great. Let us calculate the area quickly of that rectangle, and I can put some variable with me and I can maximize that variable out with all such possibilities. And this is going to work. Why? Let us go back to the problem and generalize this quickly. Why will this whole solution work considering that points is very, very low? If you want to explore all the possibilities, what would happen is you would of course start with a main for loop, which let's say is of index I, helps you iterate in the very first of the points. Then inside this becomes, let's say, the all possibilities chosen for the first point. Then you would again need another for loop, which helps you choose all the second point possibilities. This again would iterate to all the length of points. Let's say this is outside also runs till n, inside also runs till n. Then inside this, one more for loop for the possibilities to explore for the third point, again runs till n. And then inside this, one more for loop which runs to all possibilities to n for the fourth point selection. And then inside this also you would require one more for loop to check in a very brute manner whether all the other points don't lie in the rectangle if created from these 4 points above. So this is sort of a checking between thing. And then is where you can end your 5 for loops. So very brute force solution would be creating 5 for loops logic and working out every possible case. Now understand this, that if n being in this in this question is actually 10, what would happen is you would have a solution that runs in, this would be 10, 10, 10, 10 and 10. So this runs sort of in a 10 power 5 order. Now will this work? Of course, because you want a solution that runs definitely less than below some sort of a 10 power 6 or 10 power 8 order, and 10 power 5 order has to work. This makes sense. So that means if I would have just coded up a brute solution during the contest, I would be good to go. And this is what we are going to do for this problem. We just want to code up a brute solution. So I have just showed you a pseudo code. What we can do is actually discuss the main piece of logic and figure out how do we finally get the brute logic working. Okay, so I'll go back to the code piece over here that I've written. Very, very simple. Just how I explained the brute logic. You start off by your answer. That is the main answer you want to print. It is -1. All right. Now you have n as the point size. That is the vector of vector. And then of course, if you have less than 4 points, that is if in the starting phase only you don't have enough points to create a rectangle, you just want to print answer, that is -1, because you know you cannot create rectangle. You need at least 4 points for that. Great. Now you start off with the first for loop. This is the selection for the first point. That is all the possibilities that could have happened for the first point. Now I start off with the index called as I0, I less than n. Next time inside this another for loop is going to be from j, let's say just a numbering thing. And this j is going to be starting off with index I plus 1. Why I plus 1? Because I don't want to take same points, right? I want 4 different points. So I know that if I starts with 0 or I has started already, j should start to I plus 1. This is a small trick or small thing, general thing that we do. It's very, very simple to understand of when we want unique points selection from this vector of vector, all right, or all the points overall. This also runs to the very end, j plus plus. Then when the second for loop has ended, or sorry, you go inside the second for loop, that is where now you are exploring the combinations to first and second point. Now you want to insert all the next third point combinations. K would start off as an index from j plus 1, that is the previous j inside this j plus 1. By same logic how I plus 1 is there for this j as I, k as j plus 1, less than n, k plus plus, and then inner for loop, inner to inner to inner for loop again for the fourth point possibilities, k plus 1 to less than n. So you can understand that I have run 4 for loops in a very same base logic, and this is basically helping me accumulate all different possibilities of the 4 points I could have selected. How do I do that finally? I have created a vector over here to show you points of I, points of j, points of k, and points of l would actually be the 4 points right now I'm combining and then checking. So I would first combine them and now check. It's not necessary that they might satisfy all the conditions. That is why I would first accumulate them together and then first I can sort them. Why would I sort them? Because if I sort them out right now, then I would have the initial x values to be very first. That is going to help me find the area and later on help me to also check whether points came between or not. So this is a small trick which is going to help me. How? Let's actually see quickly. So what you'll do is after you have sorted on based of x, you can actually find out the area. If the area is -1, then you simply continue. If the area is not -1, then you check whether do you think there are some points that occur in that rectangle or not, inside that rectangle or maybe on the border or not. If it does, if this value returns true, continue again. And if both these conditions are false, only then you take the area to be maxed out with the answer variable, and then you return the answer. So these are two function calls that I've made. Let's quickly discuss them. Find area is going to be a very, very simple function. I'll quickly discuss and explain it. So find area, all does it want to do is find the area of these 4 points that were there. So what will happen is I pass this points vector, which were the 4 points. This is BL, TL, BR, TR. What does BL mean? Bottom left. TL means top left. BR means bottom right. And TR means top right. So now you should make sense that, okay, how was I judging that points of 0 is the bottom left, points of 1 is the top left, and so on and so on. I did that because remember I had sorted this vals vector. So it would have first sorted on the x value, sorted on x value first, and then y value. So if you understand that there would be, let's say, 2 points which have same x, then the y value which is lower, that point is preferred first. So that means now bottom left would of course be the point which has the lowest x and lowest y. Understand this. In the diagram, let's say I'm talking about this point over here, that is 1, 1. It is of course the point which has the lowest x, that is more closer to the origin, and then lowest y also, that is more closer to the origin again if you talk about the vertical direction. So bottom left becomes point of 0, then top left would become the points of 1 because that would have the lowest x but the highest y, and then bottom right would become the highest x but lowest y, and top right becomes of course the highest x and the highest y. So this is why the sorting makes sense. It's just a simple implementation trick. You can of course not sort it, but then you will have to figure out what are your 4 points. Now that I know what are my 4 points, all I need to check is, do they create an area for me or not? How do I do that? I can simply first of all check that those points should not match. So the bottom left point, as in the bottom, should not match the top left point. The bottom right point should not match the top right point. This is just a precaution that has been taken because if you understand this, because you are taking various combinations of all the points together, it is necessary that those points are unique when it comes to their x coordinates also, their y coordinates also, and so on, so on, so on. So just this precaution, the bottom left of x coordinate, to be specific, should not be equal to the top left of x coordinate. Bottom right of x coordinate should not be equal to top right of x coordinate. So the x coordinates don't match. That means they are kind of, you can say, separated on even the x axis, and then same check on the y. And then when I feel yes, both of them have passed, that means yes, some area is possible. The rectangle or these 4 points does enclose some positive area for me. I don't need to return a -1. So how do I do that? I'm going to return the length into the breadth. So length would be bottom left's x minus bottom right's x. That is going to be the length. And how do I get the breadth? That is in the x axis. Top left's y minus bottom left's y. So I'll actually quickly show you a simple diagram for this. What are we doing over here? What you would do is you would have these, let's say, for example, points. You will say this is BL. This is, let's say, TL, top left. This is, let's say, TR, top right. And let's say this is BR. This is bottom right. Now, first of all, what you would want to do is check whether you think that this condition does not become true. What is this condition? Very, very simple. What could have happened is that these 2 points, that is TL and BL, could actually have been the same point, as in, let's say, some point like this. So that would have majorly like not created exactly what you wanted. That is why a small check over here. Same thing that we are doing at this place for this x location. So this is the x axis. So I'm just talking about their x values. And then this is the y axis. This is the x axis. So once I've covered their x values check, I want to do the same thing with respect to their, their y values like this and their y values like this. So once I've done all these checks is when I can finally calculate the area, because I know there is some positive area that is getting encapsulated. How do I do that? I just find the difference like this. This is going to be the length. How do I do that? BR minus BL, again in x coordinates. So whatever is the x value over here, let's say this is x2, let's say this is x1. So I get the difference over here, and same thing over here. You can say from here I can get, or maybe I can even get over here. It doesn't matter. It's basically the same breadth that I'm talking about, and I get them by their y coordinates being subtracted. I take the absolute difference of them. So I get these two basically lengths, and then I just multiply them. That's actually the area of a rectangle, by the way. Area of a rectangle is simply length into breadth. Okay, so this is what we're doing over here. Hence, this makes me get the correct area. So I hope this logic should be clear. Very, very simple. You can pause the video. This is like a standard way of how we find area between 4 points. It's nothing very, very tough. And then of course, if the area is not -1, then I need the next condition to be checked. That now that I've checked that, yeah, the area does make sense. There is something that is belonging for these 4 points, but then there should no other point be present in that specific area that comes into region. So I need another function that is has between points, just a naming convention. I pass the main points again, and then I'll pass all the points, that is the main points vector, and I'll just pass this vector which has only the 4 points that are selected, that is vals. Now same thing, I get the BL, TL, BR, TR, same value, same thing again how I did over here, and then I'll iterate in every point in this points vector, and for that point I would want to check whether that point either is, let's say, equal to the already taken 4 points, then just continue, because of course you don't want to check a point that is actually the points you have taken. So it if is equal to either the bottom left point that you took, vals of 0, vals of 1, vals of 2, vals of 3, just continue. Else compare and see whether it falls within that area or not. How do you do that? First calculate the x of that, that is it of 0, y of that is it of 1. Now if that x has its presence between the x's of bottom left and bottom right point, or the y coordinate of it has a presence between the value of bottom left y and top left y, then you know the x and y, either of them, if either of them even, is coming between that whole area that we created. I'll go back to the diagram. If let's say like somewhere or the other this x comma y is falling at this location, then that's a bad sign for you. You don't want to consider, and you will return true. Alright, you don't want to consider this 4 set of points. And if for any point you don't execute return true, that would mean any point is not falling amongst the area, between that area that you created. So great, just return false. And this is going to be the final check that makes you either continue if you feel yes, it has some points coming between, else finally you take the answer, considerable answer, that is this area, to be maxed out with the main answer, and hence you print the answer back. Okay, so this is again, I verbally try to make you understand the whole piece of code. Since this was very, very simple, you can of course pause the video and create a case or some cases of your own. If you try run this out on the 3 examples, you will understand what are we talking about, because this is a very brute sort of a force solution. I just presented a pseudo structure to it, and then these checks are also very geometrical and very visualized based. So this find area check was main. You just understand bottom left, bottom right, and top left points, and this is ideally how you would want to check whether of course they do create a positive area, they are of course parallel, and so on. And then how do you cross verify that no points lie in that area. Okay, so brute solution. Now of course, when it comes to the time complexity, what do we get over here? We have this 4 for loops. So this would run in 10, 10, 10, 10 order. So 10 into 10 into 10 into 10. Now you have a vals vector that you create, and then you also sort it. So sorting is something that I added, and it was again the part of the implementation for me to make my life easier. That is why I can involve the sorting also. So this would basically log base of 10. That's the maximum points. Sorry, not log base of 10, log base of actually 4, because that's the maximum points you would have in this vals vector that you create, 4 points exactly. And then you have this area calculation, which is pretty much constant. You can see over here direct checks, but this has points again has this for loop, which was the 5th for loop that I talked to you about, where I said that okay, I would be again using one more for loop to consider all the points. So that is why this check is going to make another for loop in the 10 loops, in the 10 iterations. So this becomes 10 maximum case, this becomes 10, this becomes 10, this becomes 10, and then this thing also sort of becomes 10. So you can say that of course the superseding term is 10 raised to 5 as expected. That is why our time complexity turns out to be n raised to 5, or basically 10 raised to 5 in the worst case. And what about our space complexity? we have some extra space, that is this 4 size vector that we are creating extra, but let's not consider this since it's very small. Same thing I should say for the points also, it's very, very small, just a 4 sized array. So I can, a 10 sized array. So I can just consider maybe O of 10 as my main complexity that space that I create every time, or basically for the input value. That is all that is required. Okay, so that if I submit this out, of course we get a right solution, and this brings us to the end of our problem 2. Now let us move on, discuss problem 3. Alright, so maximum subarray sum with length divisible by k. You are given an array of integers nums and an array an integer k. What is required? Very, very simple to understand. Return the maximum sum of a non-empty subarray of nums such that the size of that subarray is divisible by k. Now a subarray is a continuous non-empty sequence of elements within an array. So they've given you a small definition of a subarray. Let us generalize this problem. You start off with this array of n size. I'll call this n. And you have array, let's say a1, a2, a3, a4, so on, till an. Now there is of course one more variable that is given to you is k. And what is that? You want to find, first of all, the maximum sum subarray. Okay, so subarray basically means continuous block of numbers. So maybe let's say I start off from here and then I take, let's say, 4 elements continuously. So that's a subarray, right? I don't want to break anywhere. I want a continuous sequence of numbers that I take. That's a subarray. And then I want to find the maximum sum subarray. So I want that subarray which has the maximum sum. But the catch over here is, all maximum sum subarrays will not work for this. I only want that subarray to be considered whose size, so let's say this maximum sum came from a subarray whose size was, let's say, sz. So the condition, the catch is, I want this edz to be divisible by k, that is sz mod k should be equal to 0. So only those sized subarrays should be considered which are divisible by k. I don't want anything besides this. Okay, so definitely a very, very fun problem. Let us see the test case and quickly understand this. So let's say I've given over here example 2, -1, -2, -3, -4, -5, k is 4. So I technically want an array which is divisible by 4 size. So I can take the first subarray of 4 size, that is -1 to -4. The sum turns out to be -10, and of course the size right now is 4. So 4 is divisible by 4 itself. So yeah, great, good to go. The answer turns out to be -10, and this is arguably the best we can do. If you apply the same logic over here, k equals to 2, then we can take the 4 size subarray starting from 1, 1, 2, -3, 4. The sum is 4, and 4 is the output, of course, but the size 4 is also divisible by 2. So this makes this subarray good to go. It's great, it's divisible by k, the size, but the sum is 4, and we print 4 because arguably that's the best we can do. Okay, so now that we have understood the problem, let's actually quickly glance at the constraints first so that we don't build any redundant ideas. N and k both are in 10 power 5 order. So if you might think that, okay, great, what if I would have written some sort of a brute solution, as in, I just need the multiples of k to be checked. Is that right? Right. A general brute solution might come to mind that, okay, if k is 4, then great. I would check all the subarrays with 4 size. Then maybe I can check all the subarrays with 8 size, 12 size, 16 size, and so on, so on, so on. How about that? That's sort of a brute solution. But this is not going to work, because what if, first of all, you have k equals to 1? What is going to happen then? Let's understand this. If you think this brute solution is going to work, if k is equal to 1, in this case, which can of course happen, you can understand over here, k starts with 1. So what would happen is, you would have to check the sub-array sizes of 1, 2, 3, 4, so on till n. So this creates sort of a solution that of course goes greater than n complexity, or some sort of a complexity that should remain the boundary. To be specific, this would go somewhere in an n square complexity, because you would need one loop that runs to the current subarray size that we want to check. Let's say I want to check a size of 3, great. And then you will also want one more for loop inside this, which would actually make you check the sum for 3 lengthed subarrays. So that would again create an order of n. So one n order coming from here and one n order coming from here would create an n square solution. This doesn't work. That means if you think you can brute out the multiples of k, that is not going to be the answer over here. Okay, so we need some better way, and this is where the main logic or the main idea is going to come into picture. This problem since requires sum. When I looked at this problem, my main intuition was, okay, if I'm trying to first of all find a segment sum to be specific or a sub-array sum to be specific, I know that prefix sum concept makes my life easier. Okay, this is one of the concepts that we actually teach in TLE level 2. So make sure you check this out. Prefix sum is a concept that actually makes our life easier to calculate segment sum. What would happen is, let's say you have an array that has the numbers A, B, C, and D. The prefix sum array created out of this array would dictate that I would want every ith index in this array to have the sum till those, the sum of the elements till that index cumulated. So this becomes A, this becomes A plus B, this becomes A plus B plus C, this becomes A plus B plus D, C plus D. Now why is this helpful? Because now if I would have asked you, give me the quick sum from the segment B to C, then you can be like, okay, how do I get this in prefix sum? I calculate the sum till the end of the position that I wanted to calculate. Let's say this is R location, this is L location. So the prefix sum value till R calculates the sum, that is A plus B plus C, this location. And then from that, I would subtract the sum that falls to L minus 1th location, that is minus this location, that is L minus 1. And if I do that, I get actually B plus C. You can just do this quick calculation. And isn't B plus C that you wanted? Because for the green segment, the sum was actually B plus C. So this is a very, very important concept. And you can understand how is this helpful. Because this prefix sum array can be pre-calculated, right? You can pre-calculate this array on the whole logic. And you would be good to go. Because now if I ask you, get me the sum from this to this, L to R, whatever LR being the input, you can get this sum in O of 1 quickly because everything is pre-computed. All you want is to access those indexes and figure out the answer by subtracting these, like the second value from the first value. Or you can say prefix of R minus prefix of L minus 1. Okay, so this is one of the starting points where you can start off this problem with. Now, understand this further, that if I go back in the problem, you want to check for lengths which are divisible by k. So visualize this thing. That was my next intuition. Let's say this is the array A, and let's say this is A1, A2, A3, A4, A5, A6. So let's say currently you're standing at A6. Standing at A6, let's say K was 4. So would you not want that, assuming A6 is the last element you take in the subarray, assuming that let's say A6 is the last element, you would want that you check for a subarray length that is exactly 4 length back. So maybe till this much length. This is what ideally you would want. But because you also consider multiples of 4, what could have happened is, let's say I take a better example. Let's say A is there. This is A1, A2, A3, A4, A5, A6, A7, A8, A9, A10, something like this. So now that you know that, okay, I would have, let's say I stood at A9. So this is the last number that I consider in my subarray. So technically 4 elements back is this location, but I could have also taken 8 locations back, since 8 as a subarray length is also divisible by 4. So this could also have been the end of my location. So can you see these are the two possibilities that I could have taken, standing or saying that A9 was the last of my subarray. Either you would have taken the subarray that accumulates from A6 to A9, or you could have taken the subarray that accumulates from A2 to total of A9. Okay, so now the argument comes is, what do I take? This is actually my problem, right? In the initial solution that we discussed, a brute solution, if you would have started at A9, you could have simply said, okay, why not just go back to this location and then this location and then this location? That is sort of a thing that we are trying to not do, because that creates extra time complexity. What if I have something on top of the prefix sum so that I can get this whole idea working? Now understand this greedily, that if you consider this value as A of R, that is the, or not A of R, sorry, you consider this, that okay, the prefix sum till here was, let's say, pre of R, then ideally you want to check quickly with this location or this location, right? In this case, 2 possibilities is what I could have drawn, but then there could have been more possibilities that come before this. Now the argument is, greedily, don't you think the possibility out of all such possibilities that fall before pre of R to take in the prefix sum array would actually be those possibility, or that possibility, sorry, only, which has the minimum prefix sum till that value. Why? Because if let's say this is pre of R, and from this pre of R, so this is like pre of R, from this pre of R, you want to subtract something so that you get something which is actually the sum. Now, will you not want that if this is the value I want to subtract, if this value is very, very low, if this is the lowest possible value, then this will automatically make the final value to be very, very high, because you're subtracting a very low value from a constant thing that is pre of R. So of all the possibilities that could have fallen at 4, 4, 4, 4 places, 4, 4 jumps before the A9 value, I can take only that possibility which is the minimum. And to do that, how about I don't make the jumps, rather I maintain one more array with me which I can name as, so this is a prefix sum array, maybe I can name some array as minimum prefix sum array. And what would be the target of this prefix sum array, minimum prefix sum array to be done? This array would be maintained so that standing at any location R or standing at that any location, I can figure out that, okay, take a difference of, in this case, let's say k was 4. So 4 places back or up to 4 difference back, what was the minimum prefix sum that was available for 4 places, 8 places, 12 places, 16 places, and so on, so on, so on. This gets stored somewhere with me so that I can quickly get this value. I don't have to think any further, and I will have, obviously by greedy logic, gotten the best possible possibility. From that, I can just say that, okay, subtract this value. So this value becomes the lowest possible case. So let's say that lowest possible case is mi. I just subtract this, and this becomes my definite sum, which I know is coming from a subarray which has the size definitely divisible by k. It could have come from a size that was 8, it could have come from a size of 12, it could have come from a size of 16, it doesn't matter. I just took the lowest of those possibilities. I just made sure that those possibilities are divisible by k. So I know this possibility mi is coming from a array length that is divisible by k. In this case, let's say divisible by 4, for example. Just need to calculate that sum and just max that out with some answer variable. Okay. So this is the main idea. Let us try to actually look into the sample cases again and understand this. How am I going to implement this out? Okay. So let us take this third case and understand this better. -5, 1, 2, -3, 4. Okay. This is going to help us do a lot of stuff. This is -5. So I'll do this with a different pen. -5, 1, 2, -3. And I think this is 4. Yeah, great. So you have n equals to 5, all right? So I can make this one base index 1, 2, 3, 4, and 5. And then k, of course, is given to you is 2. So you want two multiples. The size should be of two multiples. Either you take a size of 2, 4, and so on, so on, so on. Now you create a prefix sum array out of this and a minimum prefix sum array out of this. We can take the size of that prefix sum array first of all to be simply n plus 1, so that you take all borders. So this is index 0, this is index 1, then index 2, index 3, and then this is 3 can be drawn over here. This is index 1, this is index 2, this is index 3, and then this is index 4. So this is the prefix sum array, and this is the minimum prefix sum array. So you can create same length almost. So you can say this is like 0, 1, or later actually you will understand. So I think I named it over here. This becomes 4 and this becomes 5. Now you can do the same thing with minimum prefix sum array also, same length, but actually later we realize we don't need that much length. But just for now on, you can just understand same length. This is 2, this is 3, this is 4, and this is 5. Now in the prefix sum array, I want to calculate the values. So I'll start off by saying, okay, this value is 0, because if you're not considering any index as of now, you're starting with the 0 length. Basically the sum right now is 0. Then sum till the 1th index is -5. Sum till the 2th index is actually -5 plus 1. This is -4. -2, this is going to be -5 now. All right, -5, and then this is going to be -1. So this is the prefix sum array. I'll call this like PS, and this is the minimum prefix sum array. This is like mi of PS, minimum prefix. Now, what is the value I start off with over here? I start off the value. So understand this very simply, that initially all the values in minimum prefix sum array should be very, very large. It should be, of course, very large, because right now nothing has been declared. And since you want to minimize later on, you want to take the best possible cases, it should start with a very high value. So you can say that everything starts with 1E18, right? Something like a very large value, 1E18, 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 1E18. But now for the first value, that is at 0th location, you don't want 1E18, rather you can update it to the value of 0. Why do you want this value to be 0? Because right now, minimum prefix sum of 0th index denotes the same logic as how we did with prefix sum of 0. It denotes that if nothing has been taken, you are considering no size, then the minimum prefix sum array is also going to have the value 0, same how prefix sum had 0 because you had 0 sum. So this makes sense. This is the initial calculation that we can do. Now understand the logic. We start off with the first location, and now that we are not bothered with the main array anymore, we are going to talk about prefix sum, so we can go to the first index. This is the index right now standing at. And you of course have an answer variable that you start off with. What do? You say, okay, standing at this index, the index value is 1. I take a mod with k, that is 2. Why do I do that? Because I want to find what is the leftmost jump that I would have made in segment wise, and mod value is going to help me calculate that difference. So 1 mod 2 basically gives me 1. Now I'll say, okay, if it gives me 1, basically I would want to ask my minimum prefix sum array what is stored at your 1th location, because that is going to tell me that if this was considered P of R, then something left to the taken as best possibility case would be given back to me with the minimum prefix sum array. But if I actually look in the minimum prefix sum array, 1th location hasn't been declared any value as of net. That is why it has 1E18 saved. So rather not calculating anything as of now, I'll just update this to be the current value, that is -5. Alright, this is minimum as compared to 1E18. So a minimum check on this remains and works well. Great. Now I'll go, and this is like where the main logic can start working. I'll start at the second index and do the same thing. 2 mod 2. This gives me 0. What does this tell me? This tells me that now the minimum prefix sum array should at the 0th index give me a value which tells me that if you would have made a jump of multiples of 2 in the back direction, considering this is prefix of R, then the best possible case would have been that value. And now the value stored over here is actually 0, which is not 1E18. I can use it. And what would that physically mean? I am calculating, like I'm talking about this segment over here. That is of course of 2 lengthed. Till this location, I have a -4 sum, and till this location, I basically have a 0 sum that was actually stored at this or this. So how do you get this? You get this by simply saying value at this is -4. -4 minus this value is actually 0. So you get basically -4 as your answer, and your answer becomes -4 as of now, which is of course larger than whatever initial minimum you stored. Answer was very, very low initially because you want to maximize it. And this is how you tackled this case. Now the question comes is, do you make an update? As in 2 mod 2 is actually equal to -4. So do I want to make an update? As in, do I want to replace this 0th location with this value 0? Do I want to make it -4? Answer is yes. Because remember, you are maintaining minimum prefix sums for the mod values in this minimum prefix sum array. So right now, this is 0. You have -4 as a prefix sum. -4 is lesser, so updated, this becomes -4. This actually helps me that later on, if I would want to consider modular values of 0, then the best location jump in the multiple of 2 I would have made would have been to a prefix sum possibility of -4. So let's consider that. This is what I'm saving as of now. Great. Move on. Go to the next location 3. Standing at this, the prefix sum is -2. The index becomes, you can take this, 3 mod 1. Mod 2. This gives you 1 value. So what you will say is, okay, I've gotten a 1 value. So the minimum prefix sum array should at its 1th location tell me if from this being PR, prefix sum of R, what's the segment in the multiple of 2 I should consider in the best possibility greedy case with a prefix sum as that value, and it will say consider the case that is -5 prefix sum, which would indirectly mean I'm bothering about this segment over here because this segment length has a prefix sum of -2 and minus this segment length has a prefix sum of -5. So very easily visualizable. I'll say, okay, -2 minus -5, -5, this becomes +3. So I'll update the answer. Yes, it's updatable, -4 to 3. Definitely a jump, maximize it out, and good to go. Now, do I save this value back? That's the answer. That is, do I save -2 value back at -5? No, I don't do that because -2 is larger. I want to maintain minimum prefix sums. -5 is lesser. Don't do that. Great. Just move on. Go to the next index, index 4. Same thing again, -5 over here, and 4 modulo 2 basically gives you, so 4 modulo 2 basically gives you 0. So ask the minimum prefix sum array, what is stored at 0th location? That would tell you that what segment jump should you consider. In a multiple of 2, it will say -4 is the prefix sum. That's the best case right now I have. Great. -5 minus of -4, you get basically -1. You don't update it, so because 3 is still good to go as in front of it, so don't bother with that thing. But you actually make sure that this -5 gets updated back to -4 because we want lowest minimum values. So why not? -4 will get updated. It no longer remains, and you take a -5 value that is updated. So it later helps you calculate. Now that we are at the last index, so it doesn't make a lot of sense. You stand at the last index now. This value, the index is 5, so you get 5 mod 2, and you do equal to 1. And now you ask about the minimum prefix sum array. What is that best prefix sum I would get from all the possibilities if this would have been P of R and you would have taken jumps of multiples of 2? So it will say -5, which means what am I talking about? Am I talking about this case? Yes. And this is working because understand prefix sum till here is -1, prefix sum till here is -5, and the length between this is actually 4, which is made sure by the modulo values. Hence now you can visualize why did I take modulo in the first place. So 4 length, it actually works. It is divisible by 2. Good to go. Get this value -1, get this value that is -5, and you get the answer that is 4. Definitely updated. It's better than 3. Answer is 4. And then possibly you can end your algorithm now. It doesn't make sense any more updates. So of course you would do updates, but it doesn't make sense to do anything more beyond this. And yes, you get the answer as 4. Okay, so now that you, as the first precedent I said over here, if you realize back in the minimum prefix sum array, because of this modulo thing that I'm doing, I'm remaining in the range from 0 to 1. To be very specific, I'll remain in the range from 0 to k-1 only. So maybe I don't create just to save space. I can just omit these values if I want to save space, of course, because I am not using them at all, but it's fine. Even if I don't, then so, okay, great. So I hope the question was clear. You can of course take some more sample cases on your own and draw this whole simulation yourself, and you will get what do we mean over here by taking this whole prefixing something. Just repeat the whole idea once more. Started off with an intuition that I want segment sums to be very, very quick calculated. That's why I went to prefix sum, but later understood that, okay, standing at some prefix sum prefix of R, I would want the possible best greedy case which comes at a multiple of k. To do that, rather than making the jumps myself and doing this in a higher time complexity, why not create sort of a minimum of prefix sum array to get this value quickly at a difference of k back. And this is what I started saving in this minimum prefix sum array, which quickly retrieved to me that, okay, standing at this location, what best segment of multiple of k you should take for a prefix sum, and get that value, do the calculation, and maximize your answer. Okay, so let us see the code part now and understand this quickly. Just how as I told is what I'm going to do. N is there. Take the prefix sum. It is of n plus 1 size. Minimum prefix sum of k plus 1 size. Calculate the prefix sum, 1 based index, but nums of I minus 1 because nums is 0 based index. I multiplied this with 1 LL. This basically means I'm converting nums of I minus 1 to a long number, which is of course done to omit any overflow or any other structure, and basically everything remains in long. Very, very important trick. You can actually note this down. How do you convert numbers quickly? And then you start off with an answer variable. Of course, we will have this initial initialization that, okay, once prefix sum starts with 0, but every value in minimum prefix sum should be a very large value. So it can be 1E18, or you just take long max. And then the first value minimum prefix sum should actually be 0 only, right? So I initialize it back. Answer starts with, again, a minimum value that is very, very low because you want to maximize the answer, long min. Start off with the for loop, 1, 2 less than equal to n. Calculate I mod k. And if you think it's not currently long max, that means it's calculated, it is usable. How do you use it? Answer becomes max of the answer till that, the prefix sum till that is prefix of R or prefix of I, basically, ith index where we were standing at, and minus minimum prefix sum of I mod k. So the best possible jumped prefix sum you could have gotten. And then update that answer with a minimum check again. So that minimum prefix sum always maintains at I mod k location the best prefix sum. And when you finally end this for loop, return the answer. Okay, so now what is the time complexity? You have n order over here. Okay, and then you have an unorder over here again. So you can say that overall everything inside this rest is constant. So I can say time complexity is O of n. And what about space complexity? Space is also, you can say like O of n only, because n is the dominating term out of k. Or like you could consider this, yeah, it's definitely the dominating term. So space complexity is n for the nums array and maybe n again for this prefix sum array. So overall, we understand that they have shortened the time complexity from that n square sort of something that we could have gone in brute to O of n. Definitely works out for us, and this helps us solve the problem. Okay, so let us move on to our final problem, fourth problem. Okay, so the final problem, maximum area rectangle with point constraints 2. Okay, so now this was relatively a tougher problem. It's basically the second part to the first problem. All right, and why is it tougher? Is because the problem is exactly the same. So I won't repeat what are we trying to do. You just want to find the same thing for coordinates. You get the points, create a corner, and get the maximum area rectangle. It's just that now the constraints are very high. They are actually in 10 power 5 order. Because of 10 power 5 order, understand this, that even an n squared solution will not right now not work. We created a solution that was somewhere in n power 5 order, so we had lots of margin, but right now we don't have enough margin. We can only create solution that either looks in like O of n order, or by experience O of n log n order will also work by 2 power 5 order. But as soon as you go in some like n square order, that's all totally blank away. You will not be able to get n accepted on this problem. This is where the whole complexity lies. This is where the whole problem becomes a bit tougher. Okay, so let us take the problem now. Of course, I don't want to discuss the problem again. The problem is simple. Just calculate the area of the rectangle as we expected from problem 2. They have just done one extra change to this, is that the representation of the points has now changed. Initially, they gave you a vector of vector where you can take 1, 1, 1, 3, so on, so on. Nothing, no big deal. They have done over here as they have separated the x coordinates and y coordinates. So basically 1 of 1 is now this coordinate. Then you can have 1 of 1 comma 3, 3 comma 1 and 3 comma 3. So it's basically every x coordinate of I, y coordinate of I creates a coordinate together. Well, it's a very simple representation. The main idea is, let's now try to discuss. So first of all, in this problem is observations are very important. Okay, what do we finally want to get, and how do I make my whole strategy of calculating the area much more faster and much more efficient? So idealized thing over here is like I'll take this diagram. So this is 0, 0, and I've drawn an axis. So this goes an axis. This is like an axis of x, and then this is like an axis of y, and then this is the axis of x. Now understand over here is one thing that I want to do, or I started off in this problem was, okay, you don't want to make the rectangle such that there is any point inside us. Now, what does that mean? That means, let's say I'm only talking about, I'll simplify my life and I'll only talk about the y direction now. So let's say in the y direction, there are some coordinates. So I'm just talking about the y direction now. So let's say there's a coordinate like this, and let's say like this. So now this is the, if I only start considering the y direction, so I can say that this is one y axis that I want to cover. This is one y value that I want to cover. This is one y value that I want to cover. One y value I want to cover. And you can say, no, not this one. This is one y value I want to cover, and this is the y value I want to cover. Now, what do you mean by this is, focus now, like I'll try to focus now on the axes of this y coordinates only. So what I'll do is I'll say, okay, for a y coordinate 1, 2, so this is 3, I'll skip 3 because there is nothing on 3, 4 and 5. Let me say I'll collect all the x's that belong in this y coordinate. So what might happen is, you can say there are some more points that are there in each and every y equals to 5, y equals to 4, y equals to 2, y equals to 1. So maybe you have more points. Let's say you had this point was already there. So I have this point, maybe I have this point, maybe I have this point. Now with this point, let's say maybe I have, let's say maybe this point, let's say maybe this point. Great. With this point, let's say I only have this point, and then I have, let's say, this point. Then in this point, I have this point, and let's say this point. So now what I've done is, I first focus my energy on all the y direction. Now I said, let me say that in some data structure, I'll be storing all the values or all the points cumulated together for a single y. So I'll say these 2 points are basically going to be stored, or I'll do this with this pen. These 2 points are basically going to be stored for y equals to 5. What would that symbolize is I have somehow collected the points which are having y coordinate as 5. I'll collect all the points which are y coordinate as 4, collect all these 3 points which are y coordinate as 2, and collect all these 1 points which are y coordinate as 1. Now, how will that help me? Understand this over here, that if you are representing a rectangle, like if you're representing a rectangle like this, okay, then in this rectangle, right now what I'm trying to focus is, I am focusing only on the top boundary of the rectangle. So I'll take this actually to the new page. I'll say that if my rectangle looks like this, okay, like this, what I'll focus right now is on one boundary of the this rectangle, and this boundary of course is some y coordinate. So I'll focus, let's say, on this y dash coordinate right now. In this y dash coordinate, I of course want one x like this x1, and like this x2. So what I can do is I can say, okay, let's just say in momentary time that you are considering y equals to 5 as the line, the upper line y dash. Okay, let's say this is something that you are considering. So if this becomes y dash, then what is the possibility of x1 and x2? Answer me this. Understand this. Let's say over here you had more points. Let's say I'll take like this. There is one more point like this. Now you have 3 points over here in this y equals to 5 axis. You of course want something to be x1 and something to be x2, so that you have this top edge fixed. Now, because you don't want any point to come within the rectangle, if I take x1 as this and if I take x2 as this, can I say that this middle point is actually going to fall between x1 and x2? Yes, it is. That means, understand this, if this would have expanded to more of the, I don't have the space to draw this on the screen, but let's say there were more points on this. Let's say there were like 9 to 10 points there more on this whole y equals to 5 coordinates, y equals to 5 coordinate that you have drawn. Then would you not want to consider exactly adjacent points to be x1 and x2? Why? Because if you do that, then at least for this edge, up till this much location of edge, you know there is nothing falling in between. This should make sense. Okay. So I can take that makes sense. I should take x1 as this and x2 as this. So this is one of the case. Let's say I take x1 as this and x2 as this. Next time I can just shift these two locations and this becomes x1 and this becomes x2. So basically I will start taking adjacent x's on the same y. This became my first observation, that okay, take adjacent. So first thing was collect all x for a y, and then take adjacent x's for a y. This makes x1 and x2. That is like the top left points x coordinate and top right points x coordinate. Great. So now the question comes is, okay, you have taken the top. Let's say I took this as the top. I think do this with a different pen. Yeah. Let's say this is x1 that I took right now. This is x1 that I took, and this is x2 that I took. So basically this creates the top portion, top edge. Now, because this is the top edge, you of course have to create a rectangle. So this has to fall somewhere, right? From this, if this is the top edge, you need to find a bottom edge. Now the bottom edge has to be found by what paradigm? Understand this. First of all, this bottom edge, if x1 is over here, then you of course want this edge finally. I'll call this x3, x coordinate, this is x3 and this is x4. So you want to remain on the same direction from, I'll draw this with a different pen. You of course want to remain in the same direction from x1. If you're standing right now with this as x1, then of course you only want to bother yourself with the points which are of the same x value. That means this x3 should also be equal to x1. This makes sense because that is how a rectangle will work. This should also be x1 in terms of x coordinate and this should be x2 in terms of x coordinate. But the y might change. So this is y dash right now. This is some other y. And this is, let's say, y double dash, which is actually coming below y dash. So first thing is clear. I want to choose in the same direction only in x1 so that x remains same. That is why I'll get a parallel edge. Same with x2. Now, when that happens, I know this is clear, but how much do I want to go down? if at x1 standing, let's say this is an edge that was possible. So you took it. Okay, great. Let's take this. Let's say this is something that I took as x3 or basically x1 again. So this is my next edge. And let's say just assume for right now that you had one more point over here. So you could have taken this as the next thing. But the problem right now is, don't you see you have some points that are falling within the rectangle now? Because you have created a rectangle, by the way, right? You know that you fell up to a limit, which was x3. You fell up to a limit, let's say this was x4, and just assume for the fact that their y double dash also matched. So this created an edge, but something falls in between. How do we avoid that? We can avoid that by simply saying that from this x1, let's just say that over here, I had, let's say I'll remove this point just for the sake. What I'll do is, quick example. Let's just say that I had a point at this location. And let's say I had a point at this location. And then I had a point at this location also. So now tell me, from x1, when you are coming down, will you not want to stop at the first point you find? How will that be greedy helpful? Because if you stop at the first point that you find, you know that in the edge that you're creating over here, you're not covering any other point. You could have taken this point also, right? You could have covered till this location also, but that would have not worked because this point comes on this edge. So from x1, I want to go down only to the largest limit where I find a point which is correct, and this matches with this value. Great. From x2 also, I want to fall down to a point which is the best nearest case or largest from 0, and this is what I want to save. And then I know this is going to be my, let's say x3 or x4, something like that, and this definitely joins. Now all I want to check over here now would be that, is there something that falls between this? Is there some point that might fall between this? How do I check that? So first of all, of course, I would have first checked that when x3 and x4 are the points up till where I have fallen, their y should also match. So this y matches. So yeah, good to go. You have created an edge. This creates a rectangle. That's fine. Because of course, if let's say x4 was not at this location, let's say x4 was at, let's say, I'll rub this out. Let's say you had x4 at this location, right? Then you know, then this cannot create an edge. So this is the problem, right? So of course, x3 and x4 as in these coordinates should have a y which matches. So let's say I want to take the best point, of course, and their best point individually. Let's say this is called the best nearest point to this and best nearest point to this. They should have the same y that should match. But even after that, I need to check a little thing. So understand this, whatever I'm doing up till now is already taking a time complexity that is in O of n order. Why? Because you are, of course, right now going to each and every point into picture. Let's say you were standing at the all the points that were considerable for the fifth y coordinate right now, then you would be taking up x1, x2, then you would be shifting your focus to the next. This is like x1, x2, and so on as we discuss the edges and points. So indirectly, you would be covering all the points, which would create an O of n complexity already, and you have already covered 10 into 5 order or 2 into 10 raised to 5 order already by O of n complexity. Now that is why by experience I said that this problem will now only allow you a time complexity that is in log power more if you want to do something. And right now we do want to do something. We actually want to efficiently get our answer whether we find some between point or not. Moreover to that part, we need something more to help us get this best last point from top, best last point from top like this also. We need something like that also. Now, of course, you can run some very good sort of a logic with hash maps or preferably binary search, but a data structure might be very helpful over here, which is going to help us do that. That is segment trees. Why segment trees? What can we do with segment trees is, how about we do like this? I'll take a different pen, let's say a green pen. How about I compress, listen to this very carefully. How about I compress all x points together and give them an index. Give them an index. What will happen? What do I mean is, all the x points right now at this location will be given the index 1. Okay. All the points on this will be given the index 2. So all these 3 points, all of these 3 points will be called as index 2. Now all these points will be called index 3, index 4, index 5, index 6, index 7, and so on. Now what I'll do is, on this indexed array that I've created, I will create a segment tree. And this segment tree is going to save for me. What will this segment tree save? Or what will this help me update? This is going to be a point update on the segment tree. Point update on segment tree. What will this help me do, and why am I considering segment tree is, I can maintain best y coordinate for each index representing its set of x coordinates. Okay. Now what do you mean by best y coordinate? Best y coordinate means, right now when you were exploring, let's say, the 5th coordinate, so for the index 2, the best y coordinate was this. For the index 6, the best y coordinate was this. For the index 7, the best y coordinate would have been this. That's the top, right? That's the top preferable coordinate. So I'll say this position is the best. Just, I think I rubbed it off. Yeah. This position is the best. For index 5, this is the best. For index 4, this is the best. For index 3, this is the best. For index 1, this is the best. Now, all the green markers that I've done are the best coordinates. When you are now exploring the coordinate y, then what you can do is you can simply ask yourself that, first of all, let me quickly get by a segment tree, remembering that segment tree is going to answer all the queries to me in a, remember, log base n factor. This is again an advanced data structure, so you should already be aware of this part, unless this problem will become very, very tough. We understand that log n is something I can get retrieve back when I query. So I'll query and I'll say, okay, for index 2, tell me what's the best y. It will return to me this value. Fine, it returned that in log n. So I don't need to run any extra algorithm, any extra hash maps. It gets me the value quickly. Then for index 6, I'll say, get me this value. It's going to fetch back. Great. And now I'll just compare. Do their y match? In this case, they of course match. So yeah, let's move on. But one last, you can say, check. Is there anything that falls between? How do I do that? Great. Isn't this a range? Don't you feel that since I created a segment tree for this index 2 and this index 6, all the indexes that are between this is a range. And in this range, what do I want to check? I want to check that is there anything that falls in this range which gives me a y which has the best possible answer and it is falling above my edge drawn currently. So what I can do is I can say, get me the max y from 0 in this segment 2 to 6, or between, actually not 2 to 6, above 2 and lesser than 6, and it is going to return this to me. And the point it returns, the y it has given me, is actually greater. This y is actually greater than this coordinate. So I know something has fallen between it. That means everything I started off with, that was x1 and x2 right now, which I was considering, although their y is fitted, but something came in between. So I cannot consider this area anymore. I would have only considered this if their y would have also matched and there was no point in between, as in, let's say maybe the point was actually there. So the best answer you would have gotten right now would have been, let's say, this value, because this is the largest y from bottom, and this y value actually falls below the edge. So yeah, you're good to go. And this is the whole idea why we are using segment trees, because it is helping me do two things. First of all, it is helping me get the best y's, of course, for x1 and x2 when I consider some pair right now on some y that I'm doing calculation with. And later on, it helps me get this check quickly also, that if I did take these x1 and x2, the range between them, that is excluding those two, the range between them, do I get a y value which actually makes me intersect or create an edge which is above? If it is, don't take x1 and x2 into consideration. Don't create out of that a area of rectangle. And this is the idea why segment trees is helping me calculate the ranges. And like when I had this whole idea of ranges is why I went to segment trees, because I realized that, okay, between x1 and x2, there's a range I'm talking about. If I'm somehow able to get answer on a range quickly, then this will help me. So that means this segment tree will basically be a max segment tree of a basic point-based update, right? Point-based update you are going to maintain max means, of course, the best y coordinate. Why am I taking max is because from 0, you want the largest y's. So from 0, if let's say the y has to be compared, you want the better y's. Better means maximum y's. So you maintain a max segment tree. And then we only need point updates because we are not updating a range. Remember, when you would be standing at some x, like for some, let's say, when we were talking about calculating the answer for 5 coordinate, you would have already updated all the points that would have fallen before it. So those updations would have been single updations because let's say you explode 1, you explode 2, let's say you had already explored 4, then you will simply go to its point and update its y right now. So it's going to make a point update and automatically update the segment tree. Okay, so this is the idea. Again, a very advanced idea. All right, I should not say this is a very big definite problem, and this should make sense because this was 8-point problem. So it's expected that these problems are that hard. If some beginner is watching this, first try to encapsulate and absorb what is a segment tree and how do you get this ranges thing into picture, and later on draw this diagram for yourself and understand what I'm saying. Basically, going to every y coordinate and then from that y coordinate comparing all the best y's in down position is going to help me. And to do that, I am making my life easier by segment tree because it is going to help me get the best y's possible for the x's I select, adjacent x's I select, and also help me check that between thing that I don't want to get. If everything satisfies is when I finally say maximize your area with this area calculation. Now the area calculation is going to be very, very obvious as we discussed in the second problem. Just take the length and breadth multiplication. Okay, so let us see the code now. So I have taken a segment tree template over here. This is a very standard template that we use. The node over here is constructed by a merge variable. Merge function is basically taking max of left and right nodes. That is why this would be called a max segment tree. And this is a point update that is simply updating, let's say the new value whichever comes to be the previous value gets updated with the new value. So a single point update. And then as a segment tree, you have a constructor over it, you build it out, you update whenever you want to, and you query whenever you want to. Now, this is the main idea. Understand this very, very carefully. You first of all take n size, that is x.size. Now you have a map of int comma vector of int, which is called all x for y. What is the meaning of this? As I started, you first of all want to collect all x's for a single y. So to do that, I have this, and then I have a set of all x. What is that? This is basically the compression that I'm talking about. So again, you want to name that, okay, all x's have been named as the index 1, then all next x's are index 2, all next x's, x coordinates are index 3, so on, so on, so on. So I have that set for that. Why set? Because set is going to help me remove the uniqueness, because I know that, let's say I'm talking about all these 3 points. These all 3 points are basically on the same index 2. So I need to collect them, and if they repeat again, it doesn't matter. Great, good to go. So I'll make a set out of it. Run a for loop. For every y of I, push back that x of I in that map. And then in all x of set, insert that xi value. Now I have a total x variable, which basically means how many x points are there. So in this case, let's say you saw that there were 7 points. So that is going to declare the size of the segment tree. So for that, I have a total x, starts with 1. I have a map that is all x to index. I need this mapping later on because I need to quickly call the index that were collected for every x value. So I'll say run a for loop in the set. For every x value, make that x value mapped to the index, and index gets plus plus, or length basically gets plus plus. Later on, create an array of this much size, total x plus 2, starts with all -1. Why -1? Because -1 is going to help me maintain that checker of max, like area wants to be -1. So it's just basically a checker of if you don't find, then you want to return a -1. Now you create a segment tree out of this. So I call the struct variable, I pass this much, and I pass the array. Now I have a segment tree ready right now, which has all -1s. Then what I do is I have an answer variable, that is the main area that I want to print. I go to every auto p in all x of y. So basically I first extract, like since this is a map of integer comma vector, so first is going to be the integer, that is actually the y coordinate, and the second is going to be the vector, that is all the x coordinates for that particular y coordinate. Then what I can do is I can sort them, so that I have basically, I can now start taking adjacent x's. And then what do I do? First of all, a very, very simple common sense check. I think I missed this part. Of course, you need more than 2 x coordinates to fit your whole thing. If let's say on a single y, you only have a single x, then you cannot take 2 points. You need to check adjacent points. There need to be 2 points at least. So the size has to be greater than or equal to 2. Then you go inside the for loop, and then you say, okay, start taking from 0 to length -1, and I and I plus 1 are the adjacent things I take. So first of all, I make a query. I take this as the last one and last two variable. What does that mean? I query in the tree for the L to R range. I say I want to query a single, since this is a point query, so you will pass all x to index of that. So this all x to index basically returns the index to you. So let's say you're starting at x1 point, you return the index 2, and from where to where? Again, to index 2 only. So this basically makes a point query to 2 to 2, which would make sense because all you want to find is the best y that was for x1. So you'll say, okay, pass 2 to 2, dot value is going to return the value to you. So this gives me the last y value or the best y value by the max function. Do the same thing for this next coordinate. So if I have done this for x1, I want to do this for x2, that is I plus 1. So do the same thing, get the index and pass that same index in R also. So L to R, same range. When both queries have been made, first check is last one equals to last two. So of course these two y's should match, else they don't create an edge which is parallel. So if they don't match, it's a problem. So they should match. And then they should not be -1. If they're -1, that means right now you don't have anything below this to check. So both checks should be false, as in true in this case. Last one should be equal to last two and last one should not be -1. If that is the case, then I find the between points. I make a check. Is there anything between this? How do I get that? I say, okay, the index for x1 plus 1. So the index for x1 is this much, plus 1 is this. So basically query from 3 index to the index of x2 minus 1. So basically the query from 2 till 5. So you find the between points possible from 3 to 5, get the value of it, and then is that less than last one? If it's less than last one, that means this edge is coming below. So great, you can actually create a rectangle. Length becomes the difference of x2 and x1, basically all coordinate for I plus 1 minus I, and breadth becomes y coordinate minus last one. Now this could also have been last two because last one and last two are the same value. If you go inside the if check, basically it means you have the y coordinate, this y coordinate, that's, let's say we're considering the 5 case, and then this is the y coordinate you actually got. Get the length into breadth, that's the answer. And when you actually end this if check, you want to make the point updates, because later on, let's say, so as you were standing at 5, you already knew that you had made an updates for 4, 3, 2 and 1. So how would that have come off is you would have gone to every x coordinate possible, and then you would have made an update and said that, okay, the current best y coordinate for that x index should, that x coordinates index should be mapped to that y coordinate. So make an update. And since the segment tree is max segment tree, so it only makes an update when you feel that the x is better, the y for that is better. If it is not better, then it doesn't make an update. It maintains the max always. And then you return the answer. Okay, so now again, I know this could have been done, maybe let's say a very complex binary search to attain this log and factor again. But then segment trees just makes our life much more easier. And it's always better to have this on hand because segment tree questions are frequently visible in fourth problems for Leetcode. Okay, so now what is the time complexity? We have, like, you can say you have a map over here. Now map of course takes like log n insertion time every time you do this. So you can say that this is like n factor, and then inside this n loop you are basically inserting. So that is like log n, maximum log n factor again taken. And this insertion is also like pretty much log n only. So this still remains same. Now set and map has been covered. Insertions are log n complexities. Then you have again a map, same thing. You can take this as like, because you go in all x's, so maybe all x's were distributed. This could have been n factor again. This could have been log n factor again. Same thing. Then same thing over here. You are basically going in a for loop. So whatever for loop finally you go for, you know that basically you are checking for every point, and every point's queries are made in log n factor. So overall, this for loop can be written as n, that is n points that I cover, into log n, that is the queries I'm able to make and updates I'm able to make, all in log n factor. This is where segment tree held me. Effectively making my time complexity as, you can say O of n, log base 2n to be specific, which is fine. This works for a 10 power 5 order. And what about space complexity? Now I have some space that I'm going to use for the maps. Again, maximum n order, sets, maximum n order, and then segment trees. I am passing index total, index plus 2 size. It actually creates even like in the template you can see over here that we create a size to be a bit larger than that part, but then an order of n is something you can still go ahead with to write, because the segment tree also doesn't create a very high order. It basically finds the next best 2 power value to that thing, which is fine to write in an n order. Okay, so not a beginner friendly problem. First of all, requires segment trees, requires advanced concepts. And if you understand that part, this should be sufficient for the explanation. You can draw the segment tree probably on your own, maybe take some more cases and understand what I'm trying to do. Maybe take example 2, you realize, okay, standing at the third, let's say y coordinate, what happened, and so on, so on, so on. And how do we are making this sure that we take best rectangle only. Alright, so this brings to the end of our post-contest discussion. I hope you like it. Thank you for watching.